Natural convection heat transfer, part 3. Natural convection over surfaces. Natural convection heat transfer on a surface depends on geometry, orientation, variation of temperature on the surface, and thermophysical properties of the fluid. So for natural convection, we need to look into the geometry of the system. Although with the same geometry, but different orientation will be different kind of thing. And variation of temperature on the surface, and thermophysical properties of the fluid, whether it's in the air or in the water or many other fluids. The simple empirical correlation for the average Nusselt number in natural convection are of the form Nusselt number equal to H times LC divided by K. H here is the convection coefficient, LC is the characteristic length, then K is the conduction heat transfer coefficient. And this equation also equal to C times Grashof number times Prandtl number, and both Grashof and Prandtl number with the power of n. Here C and n is a constant parameter, and this equation we can further simplify it into to be C times Ra L power of n, and the RAL power of n is the Rayleigh number, which I show you in this slide at the bottom of this slide. We have a Grashof number times Prandtl number equal to this equation. The value of the constant C and n depend on the geometry of the surface and the flow regime, which depend on the Rayleigh number. So I mentioned earlier C and n. The constant C and n, it is depend on the geometry and also the flow regime. All fluid properties are to be evaluated at the flame temperature Tf, which is the flame temperature, equal to surface temperature times the infinite temperature, which the temperature which are far away from the system. The Nusselt number relation for the constant surface temperature and constant surface flux cases are nearly identical. As in the post-convection, we have two systems, which is the constant surface temperature and constant surface flux. Same with the natural convections. The relation for uniform heat flux is valid when the plate midpoint temperature TL/2 is used for Ts. So, in the evaluation of the flame temperature, so we have two systems. One is the constant surface temperature and the other one is constant surface heat flux cases. So for the constant surface heat flux cases, the surface temperature will be replaced by the midpoint temperature of the system. Thus for uniform heat flux, the Nusselt number is equal to as I show in this equation, and the constant and C and n depend on the geometry of the surface and the flow regime, which is characterized by a range of the Rayleigh number. Okay, there is a note here. The value of n is usually 1/4 for laminar flow and 1/3 for turbulent flow. So this is the table of the empirical correlation for Nusselt number average. So as I explained previously, we have a value C and n, constant C and n. You can get the value C and n here in this table. It's depend on the geometry in the first column, which is the geometry, and then it also depend on the range of the Rayleigh number. So as you can see, although it's the same plate, which is a flat plate, but in the vertical position we will use different equation compared to the horizontal plate, and same with the vertical cylinder and also horizontal cylinder. Okay, vertical plates Ts constant. For a vertical flat plate, the characteristic length is the plate height L. In table 9.1, three relations for the average Nusselt number for isothermal vertical plates are given. The first two relations are very simple, despite its complexity. The third one, recommended by Churchill and Chu, since it is applicable over the entire range of real number. This relation is most accurate in the range of 10 to the power of minus of 1 and 10 to the power of minus 9 of the real number. So on your right hand side there is a vertical plate and also the three equation. The first two is the simple equation and the last one is the complex equation, and which are recommended by Churchill and Joule. Vertical plates Qs equal to constant, which is the uniform heat flux. The relations of for isothermal plates in the table can also be used for plates subjected to uniform heat flux, provided that the plate midpoint temperature is used for surface temperature in the evaluation of the fluid temperature, Rayleigh number, and the Nusselt number. So please bear in mind that for the uniform heat flux, we need to replace the surface temperature to be the midpoint temperature. Inclined plates. In the case of a hot plate in a cooler environment, convection currents are weaker on the lowest surface of the hot plate, and the rate of heat transfer is lower relative to the vertical plate case. Okay, so although steel plates, flat plates, but the orientation give different value of heat transfer rate, which are explained in this slide. So please keep this in mind and be careful when answering a question. On the upper surface of a hot plate, the thickness of the boundary layer and thus the resistance to heat transfer decreases and the rate of heat transfer increases relative to the vertical orientations. In the case of a cold plate in a warmer environment, the opposite occurs. So same with the first video which I show you for the natural convection, we have a cold can and also hot egg. So the natural convection current is different between these two, which are opposite, and same with this inclined plate. Horizontal plates. For a hot surface in a cooler environment, the net force acts upwards, forcing the heated fluid to rise. If the hot surface is facing upwards, the heated fluid rises freely, inducing strong natural convection currents and thus effective heat transfer. But if the hot surface is facing downwards, the plate blocks the heated fluid and tends to rise, impeding heat transfer. The opposite is true for a cold plate in a warmer environment, since the net force in this case act downwards and the cool fluid near the plate tend to move down. Okay, so as we all know, a hot air tend to move up and the cold air tend to move down. This kind of thing also happen in the boiling of a water. LC is equal to the surface area divided by the perimeter, which is the characteristic line. And for a horizontal square surface of length A, the characteristic length is equal to A divided by 4. And for circular surface of diameter D, D divided by 4 is the characteristic length. Horizontal cylinder and sphere. The boundary layer over a hot horizontal cylinder starts to develop at the bottom, increasing in thickness along the circumference and forming a rising plumb at the top, which as shown in the figure on your left hand side. Therefore, the local Nusselt number is highest at the bottom and lowest at the top of the cylinder when the boundary layer flow remains laminar. Okay, this is for the case of hot cylinder, and the opposite is true in the case of a cold cylinder, horizontal cylinder in a warmer medium. The boundary layer in this case starts to develop at the top of the cylinder and ending with a descending plumb at the bottom. This is the end of part 3 for natural convection. Thank you.